How do we decide strong versus weak? Well, a strong acid and or base, and since acids tend to be the easiest one for us to address, we'll look at this. So there's a generic acid, HA, completely ionizes when it hits water. So we get H plus A minus. So that reaction only goes one direction towards products because that species we've identified as being a strong acid. That identification of it being a strong acid largely comes from establishing equilibrium stuff, which we haven't done yet as far as this video is concerned. If we look at H, let's go ahead and call it B, HB, if it's going to act as an acid, is still going to produce H plus and now B minus. So it's a different acid in this case because we're getting B minus versus A minus. This reaction is actually a weak acid. If it's a weak acid, what happens? Well, because it is a weak acid, we get the double-headed arrow, or our two arrows, one going to the left and one going to the right. Okay? That combination of those two arrows is stemming from our weak aspect. It's saying that it ionizes to different amounts. So weak acids can sometimes produce lots of H+, sometimes they don't produce that much. Okay? Strong acids always and only produce lots of H+. So it has to do with kind of the directionality of that arrow. That arrow is what is known as equilibrium, and like I said, that's going to be addressed in the next video. So how would we be able to differentiate between our strong and our weak acids? Well, the strong acids are the dangerous ones. So we tend to call out those dangers by just straight up memorizing them. So depending at what level of chemistry you need to move through, you might be asked to memorize your strong acids and bases. So here are your strong at 1, 2, 3, 4, 5, 6. There are 6 strong acids listed here. There are more than 6, but these happen to be the 6 most common. And in a class where this was expected, those were the 6 acids that students were expected to memorize. For our class, for Chem 130, we don't need to memorize those. What I want you to be able to do is to acknowledge that there's a difference between a strong acid and a weak acid. And similarly, there's a difference between a strong base and a weak base. The strong acids would be things that we would just memorize, and then the weak acids and bases would be anything that, well, wasn't a strong acid or base. And that's kind of our big conclusion out of these. You'll also note that we're seeing another kind of key term floating out here, an electrolyte. We'll define that as another term, and actually I think I'm going to do it in this video. I just may have to skip some slides around. Okay, so we'll see that in a little bit. Okay, so we've got this strong versus weak. The next thing we want to think about is safety. Okay, what makes the poison is the concentration, or how much is there. Well, we talked about concentration already in this class, and that was our units of molarity, or that capital M. Okay, so we could shout to Timmy, hey, watch out for that 0.15 molar H plus solution, it'll burn you. Okay, well, that's a bit of a problem because Timmy, number one, doesn't know decimals, and number two, doesn't know capital M. What the heck does that mean? Okay, and neither did you. So if you think about your safety and what you've gone through in your experience, really what we're trying to address is how can we get the average populace to be able to understand something about the hazards of strong acids and bases, but without making them go through a big course that addresses decimal meanings, that addresses new language, okay, capital M's and those meanings. So how do we address this? Well, think back to your knowledge already of acids and bases. Do you already know of a system that allowed you to classify different solutions according to their acidity or basicity? Hopefully, yes, you've been trained about pH. Okay, so pH was a way to convert those concentrations that are very difficult for the human brain to wrap around and convert that into a system that was easier for people to deal with. Interestingly enough, what does that system rank at? 0 to 14. Okay, for those people wondering about the numbers, 14 is just outside of our realm of understanding. Okay, but it's in that range. The decimal values were way outside of our understanding and virtually impossible to understand. So what we can go through and do is now teach a kid numbers 0 to 14. This is what we do in math classes to get you used to manipulating numbers at that scale. And we can now go through and add some extra information on top of those numbers. That low pHs, something like 0 or 1, would be acidic and are bad, quote unquote bad, or dangerous. And that solutions of high pHs, like 14 on this scale, are now bad or dangerous as well, and those would be basic. And that really halfway in between those two bads, pH of 7, would be our safe spot. Okay? And that should have been theoretically what you've seen in your past. Okay? How do we get to that? Well, we would get to that pH system and that numerical system by using a negative log of the concentration of H+. Okay, so why do we not tell students about that? Well, it introduces this idea of logarithms, which confuses people. It introduces this issue with negatives, which confuses people. Those brackets meant concentration, which confuses people. There's so many different things about that confuse people. So we just said, hell with it, 0 to 14. We've now converted the science into a format that is a little bit easier to digest. And yes, it oversimplifies things, perhaps excessively, but it at least allows a baseline that we can now have those conversations with the average populace without having to really drill into dealing with concentrations and calculations and all of that fun stuff. Okay, and just for the record, just staying inside pretty simple directions, and we can see how horribly people are following those directions. We're not going to be able to deal with concentrations, teaching that to everybody, everywhere. Second to last slide for this video, the big deal that we're getting out of this, or why we address acids, is really to get this concept of buffers. Okay, the whole point of a buffer, okay, in this case a car buffer, is to minimize the visibility of scratches and dents. The same thing happens in chemistry, except it's not scratches and dents, it's minimizing changes in pH. Okay, so minimizing changes in the acid or base content. Why is that really important? Well, we've got a big long expression written down below. We've got a whole bunch of arrows going back and forth talking about our equilibrium. And really, we don't need equilibrium to address this right now, but what these are trying to show is what's happening in our blood. Our blood centers around the concentration pretty much right in here. Okay, so what our blood does is it changes the concentrations of H2CO3 in comparison to HCO3 minus. And so there are small amounts of those substances in our blood right now. Okay, and why is this important for us? Well, let's say our blood all of a sudden goes slightly basic. In the process of it being basic, our pH is going to skyrocket upwards, and that could burn us, okay? And that would burn internally. So what needs to happen is that something would need to come along and remove that basic stuff. So if I add a whole bunch of hydroxide, what happens? Well, the hydroxide will react out with the H+. That means I've neutralized the hydroxide. Okay, it's no longer there. But I now also don't have H+. Since I'm missing that H+, my pH could potentially go up. This is where our equilibrium comes into play. The small amount of concentration I have of H2CO3 will then go, well, crap, I need to fill that hole. So it will shift to produce. So the concentration of H2CO3 will go down while the concentration of HCO3 minus goes up and the concentration of H plus goes up. This is now going to ensure that our concentration of H plus stays relatively constant, even though I've added a base. Well, what happens if instead of adding a base, I add more H plus? And go, well, the H plus can't cancel H plus, but what could cancel the H plus would be a negatively charged species acting like a base. And what will that species do? that will react with the H plus, the extra stuff, and it will cancel it out. The net result is that the concentration of H plus overall doesn't change. It stays constant, which means our pH won't change. So our buffers exist to help minimize the changes in pH. Okay? Again, why is this important? This goes all the way back to intermolecular forces. As we change acids and bases, we end up changing the charge in the solution. If the solution changes charge, all of the structures will also change their charge, and that changes how they interact with their environment. And so you can get some really massive, big changes happening. Okay? So, big deal. We see it in our blood pH. What's being shown on the far left is an example of this. Okay? What they're referencing is that we're starting with blood in kind of a homeostasis, meaning our pH is constant. What happens if the pH goes down? Well, pH going down means H plus goes up. Remember, it's more acidic. This is now known as acidosis. We have more acid present. As the acid concentration goes up, this starts to send off signals in our body. Those signals, in turn, increase respiration. Okay? That means we start exhaling. Okay? As we start exhaling more, we start losing CO2. So that CO2 concentration goes down. As that CO2 concentration goes down, that's going to now need to get replaced. And so the H2CO3 in our blood is going to start to replace that CO2. Okay? So our reaction starts to decrease the H2CO3. As the H2CO3 goes down, what happens? Well, we need to replace that H2CO3 by doing the next reaction. So that next reaction is then going to cause this H plus to go down also. Okay, what does that mean? We initially spiked the reaction by adding H plus into this. The end result at the cascade of these reactions was that the H plus concentration goes down. It counteracts the H plus spike that started the whole cascade, and the homeostasis, or our pH, stays constant. And this happens regardless of whether it's an acid system, acidosis, or alkalosis, which is in reference to our alkali earth metals, where our pH goes up. If our pH goes up, we're becoming more basic. If it's more basic, that means our H plus concentration is artificially being pulled down. What happens to it? Again, we see all the signals. Those reactions cause the cascade to shift how our reactions move through to ensure that the concentration of H plus, ultimately our pH, remains constant. Okay? Can we overwhelm the buffer? Abso-freaking-lutely. Okay? So, and that's typically when one of those systems in this process fails. Okay? And this is vastly simplified. But if one of those systems falls apart and stops actually functioning appropriately, our body can't maintain the pH appropriately, and that's where our blood effectively starts dissolving all of the biological material it comes in contact with, which would ultimately mean, well, death. Okay? And before you're thinking like, oh, you just melt, it's not that dramatic. It just means pretty much everything falls apart and stops functioning, and so you would just die. Okay? And so that's what's happening with our buffers. It's a really big deal. It's kind of neat. If you're going into the nursing field, you will be studying up the yin-yang about this buffer system, and probably 3 or 4 others that are critical for understanding both respiration and then drug dosing as well. Okay, and with that, I'm going to do a quick pause on the video so that I can skip to the electrolyte slide, because the electrolytes I think tie in kind of better with this. And then here are our electrolytes, which are a real quick kind of one-off topic that I'm not super stressed about. Okay, what we're talking about, and you shouldn't be stressed about it either, is that when we add something to water and it completely ionizes, it's an electrolyte. What did we say a strong acid was? A strong acid was something that completely ionized. So strong acids are good electrolytes or strong electrolytes. Okay, why does this become important for us? If we looked at a container, so put in a beaker, we've got some water in here, and we take some copper electrodes and we drop them in here, and we attach those electrodes to a battery, all that fun stuff, and then we put a light on the top of this. Okay? And it's a big if the circuit completes between those copper electrodes, okay, if electricity can flow, then the light glows. If the electric current can't transition between those, then our light doesn't glow. Okay, so this is why electrolytes are cool. What electrolytes are just ions, positive and negative ions. Those positive and negative ions can align themselves between the electrode, allowing for electrons to flow from one side up to the other. Why is that important? If we get electric flow, that's what's going to allow our light to come on. So we can think about electrolytes as electricity lights, okay? Literally turning on a light. Okay, why is this important for us? Well, if we think about the entire human body, how everything functions is actually through the flow of electricity. There are small electrical terminals within your bodies and nerves that are allowing for signals to be transferred. We need electrolytes in there to allow for that flow of charge. If we don't have electrolytes, then our bodies stop functioning. This is why if you've ever gotten serious leg cramps, one of the things they tell you to do is say, drink up potassium or get potassium into your body. Why? Potassium, not as the metal, but as the ion form, is an electrolyte that will allow for the passage of electrons, okay, or that electric current, which is what's going to allow your muscles to actually relax or contract. Okay? So electrolytes are very, very important. So what you need to be able to do is to look at a formula and decide if it's an electrolyte. So, sodium chloride. Sodium chloride is an electrolyte. How do you know sodium chloride is an electrolyte? You've probably already memorized that outside of the class. So let's move on to a different one. H2SO4 is an electrolyte. Why? That was one of our strong acids. As a strong acid, it is by definition completely ionizing, so a strong electrolyte. The next one, sodium hydroxide, a strong base, and because it is a strong base, it by definition completely ionizes, and so it therefore will also be a strong electrolyte. Okay, kind of bringing back the concept of our sodium chloride, calcium carbonate, iron hydroxide, and silver bromide. Well, sodium chloride, we said you might have memorized. Okay, and just knew that one would dissolve in water and get us those ions. That's how we know we broke that bond and how we know it's a chemical reaction. But how would we know, say, calcium carbonate, iron hydroxide, or silver bromide? That becomes a little bit more challenging. Really, with your sodium chloride, you're saying you knew that through experience. And really, experience is just another form of saying you've already done the experiment. Okay? Well, determining if something is an ion is also based on experiment. And you've already experienced this. In fact, you know how to identify if these species dissolve in water and should be labeled as aqueous, or if they do not dissolve in water and should be labeled as solids. That rule would come from our solubility rules. Those solubility rules are not things that I expect you to memorize, but I do expect you to have memorized that you need to use them to determine solubility for ionic substances. And when you go and look up those solubility rules, you will find that calcium carbonate, iron hydroxide, and silver bromide are all insoluble in water. Well, if they never dissolve in water, they can't be electrolytes. Okay? And this would make them either non-electrolytes or very weak electrolytes. At this stage, all I'd want you to do is say non-electrolytes. And the first ones would be strong electrolytes. So we're applying the definition of our acids and bases to our electrolytes. We're applying our definitions of solubility of ionic compounds, going all the way back to Unit 2 with our double replacements to get our non-electrolytes. And then we've got the last category down below, deciding with these. Okay. Well, none of these are strong acids and bases, though we do see a tip-off that we're looking at an acid here. We would know it is weak because we memorized that it's not one of the strong ones. Okay. How do we know whether these should be strong or non-electrolytes? They don't fit the strong definition for acids and bases. They don't fit the definition that we've been using for solubility because they aren't ionic. Our solubility rules only apply to ionic compounds. All three of those compounds at the bottom are molecular compounds. So how would we go through and classify those? Well, molecular compounds don't ionize to large extents. So these end up coming in again as non-electrolytes. The last thing I want to call attention to, which is conveniently located in that immediate vicinity there, is that I will sometimes get students saying, but isn't that substance a strong base? Don't you see the presence of hydroxide in that blue box? And to that, I will say, no. There is no hydroxide in that blue box. This becomes a really important definition that usually goes over everybody's head, including some instructors. Okay? That is not hydroxide. What is hydroxide? Hydroxide, as a formula, was OH minus. Okay? Isn't this OH? Yes. Is it OH minus? For it to be the minus, this would have to be ionic. In that blue box, those are all non-metals, which means by definition, they are not ionic. That is not hydroxide. That just is a misleading OH. Okay? So that is an important distinction to make with that. And with that, I will go ahead and end this lecture. Thank you for listening. You only have one more lecture. That is both for you and for me. Woohoo!